Hi everyone, welcome back. We are continuing with our section on u substitution, and I'd like to do a couple examples that also involve trigonometric functions. So here's one of them. We want to integrate 3 cosine x divided by the square root of sine x dx. Again, without the use of this new technique, we would be stuck. There is no quotient rule for integration. We can integrate over a sum or difference, but a quotient, a product, that's when u substitution can be very helpful if we can transform the integral to something a lot easier in terms of a new variable such as u. So what would you let u be in this case? There really seems like two choices, right? You could let u be sine x, for example, in which case the u would be cosine x dx. And you could look up there, do you see a cosine x dx? Embedded in the integrand? Indeed we do, right? In that case, we know this is a good choice. Now what if you did the opposite way? What if you let u be equal to cosine x? Then du, here you're differentiating, right? So it'll be negative sine x dx. Well, there is a sine x there is a dx, but it's not a sine x dx. It's like 1 over the square root of sine x dx. So this would not have worked. So we should really let u be just sine x. And it's important to realize going from u to du, you are differentiating, right? Whereas later on when we do the integral, we're anti-differentiating. So within the same problem, over here we're differentiating, and later on we're anti-differentiating. So very important to keep those rules straight. Like what was the derivative of sine x? And if in case you need to integrate it at a later time, remember what the integral of sine x might be, right? But in this case, we just need to differentiate going from u to du. Now, when we rewrite this problem, I'm going to pull the 3 outside. The bottom just became the square root of u, and cosine x dx is what turned out to be just du. Think about how you would integrate this. Let's write this as u to a power. U to the negative 1 over 2 du. And to take the entire derivative, I'm going to add 1 to the power. I get u to the 1/2 over 1/2, or the same as instead of dividing by 1/2, I could say times 2 over 1. So that's just going to be 6. 3 times 2 over 1 is 6, times the square root of u. U to the 1/2 is the same as square root of u, and we know u is equal to sine x. I can write this as 6 times the square root of sine x plus c. If you wanted to, you could put an intermediate step here. You could say 6 times square root of u plus c, and in the last step replace u with sine x. Okay, so that's an example that involves a trigonometric function, and we're going to do one more. And here's our next example involving u substitution with trigonometric functions. So think about it, what would be a good choice for u here? Again, typically we want to select u in such a way that its derivative is already embedded in the integrand up to a constant. So if you let u be equal to tangent x, its derivative we know is secant square x dx, so that would be a good choice. So let u be tangent x, du is secant square x dx. So this integral, now this part becomes square root of u, the 5 can be taken outside, and secant square x dx can be replaced by du. So this becomes root u, take the 5 out, and then secant square x dx has been replaced with just du. So at that point, again, I'm going to factor the 5 outside, and square root of u is same as u to the 1/2. And so we've seen examples like this, plenty of them, right? So you add 1 to the power, you get u to the 3/2. You divide by 3/2, which is the same as times 2/3. So you're going to have 5 times 2/3 times u to the 3/2. Notice no more integral sign, right? Because it's done its job. We've already taken the entire derivative. So see if you can finish the problem from this point forward. So 5 times, think of it as 5 over 1, right? So 10/3. And instead of u to the 3/2, I need to bring the u variable back. U being tangent x is going to be tangent x to the power of 3 over 2. And don't forget the plus c, no limits of integration, so we want to end it with plus c to give it the general antiderivative. So the integrals involving trig functions, they may look more complicated, but they may actually end up being easier as long as you know how to differentiate the main six trig functions. Right? You must still remember the derivative of tangent is secant square, derivative of sine is cosine. What about derivative of secant x is secant tangent, right? So it's good to be reminded of those. And then you have the cofunctions, which can be easily obtained from those three. For this one, could you have selected u be secant x? Well, if you let u be secant, this could have been u squared. But derivative of secant is secant x times tangent x, and there is no secant x times tangent x in this integrand, right? So that tells me that is not a good candidate to be u. So once again, I would highly recommend at this point to do lots of questions without trig functions and get good practice, because u substitution in a sense is kind of like factoring is in algebra, meaning it's a foundational technique in calculus. So it's going to get so much use, and all the other techniques of integration you're going to learn in Calc 2 will be based on u substitution. So being strong with that will give you a great start in Calc 2 also, in case you need to take that class.